Good evening, everyone, and welcome digitally to UCL and the Institute for Sustainable Heritage. My name is Josep Grau, and I will be the host of this talk. It is the first lecture of the ISH guest lecture program, which this year will offer monthly 8 very diverse and thought-provoking talks. They are all advertised online if you want to see the rest. This lecture series is also part of the ISH Academy. The Academy launched in 2019, and it's how we offer lectures, workshops, executive courses, and so on. So for example, there's now one in offer called New Social Futures from Heritage. It's a short course. You can also check it in our website. It's also part of the ISH Academy. I should also say before we start that this academic year marks the 20th anniversary of ISH. So we have another important ISH Academy activity that I want to advertise, which is that we are going to celebrate the Sustainable Heritage Bidecennial Conference in March 2021. I'll give a couple of simple rules of a couple of simple housekeeping rules. So this lecture is being recorded, and it will last for approximately 30 minutes, and then it will be followed by some time for questions and answers. In order to ask questions, your microphones are muted, so the method to ask questions is to record them using the Q&A button that you will see at the bottom of your screens. And then on the Q&A section, I will read your questions aloud. I'm going to introduce now Professor Dina D'Ayala. She's a professor of structural engineering at UCL in the Department of Civil and Environmental and Geomatic Engineering. She's the head of civil engineering and the co-director of the Epicenter, which is a center that investigates risks to society, the built and natural environment caused by natural hazards. She's the director of the International Association of Earthquake Engineers, fellow of the ICE, and a Getty Conservation Institute scholar. Her specialism is structural resilience engineering with emphasis on the assessment, the strengthening and preservation of existing buildings, and of course, cultural heritage. She has 25 years experience working with international agencies and heritage institutions to assess and preserve architectural heritage worldwide. Dina, over to you.
Thank you very much, Joseph, for these introductions, and thank you everybody for tuning in to listen to this talk entitled Crests and Troughs, the Survival of Victorian Lighthouses to Extreme Wave Impact. For the past 4 years, with colleagues from Plymouth and Exeter University, we have been trying to piece together the puzzle that determines the response of historic lighthouses to extreme wave loading. And in doing so, the question is, that wave breaking really would affect lighthouses for the survival for the next 250 years. Here you can see some videos were recorded along the coasts of France and Britain, which shows the power of winter storms and wave breaking on various lighthouses at sea. And one of the concerns is that with climate change and increased sea level in the future, these structures can be even a greater risk that they are currently. But why is it important to preserve them? Well, this is a shot taken, I think, last Sunday night of the traffic in the English Channel of commercial freight passing through. And while in the age of GPS, we might think that there is no more need for lighthouses, actually GPS fails, and the existence of light at sea at night is considered the major safe bet for this in these cases. So you can also see in this image here the number of lighthouses along all the coasts. This evening we will be talking mainly about lighthouses at sea. So what are the pieces of the puzzles? We are considering 6 lighthouses which were built in the second half of the 19th century, all in the care of Trinity House, which is an organization that was set up in the UK since now 500 years old, with the aim of controlling and managing the commercial and end of shipping. The lighthouses were built with dovetail granite blocks, and they were very good, but are also a very complex structural behavior. With colleagues at Plymouth, I've used statistical tools, theoretical models, and experimental work to determine the interactions of the magnitude of the waves and their interactions with both the bathymetry and the rocks and the structures built on these and built on top of these outcrops of rock at sea. Together with this on-site investigation was conducted for each lighthouse by Exeter University teams to identify their structural and dynamic characteristics, which are then fundamental to the development of individual structural models, which were developed at UCL. Among other things, I hope that you can see the right-hand side of my pictures. In case this was on top, I just removed it. Among other things, they have installed long-term monitoring on a number of lighthouses so that we can in future actually capture the strong events of wave breaking on lighthouses. The behavior of lighthouses cannot really be understood without going back to the Smeaton Hedgeston Lighthouse, which was built about 1 century before the ones that we will be speaking about tonight. The ingenuity of Smeaton should also be seen not just in terms of its particular creation, but in relation to the fact that in the previous 150 years, there were only failed attempts to install durable lighthouses on various shallow rock in the English channels. And in the following intervening 150 years, this lighthouse survived until it was removed to shore in the Plymouth harbor because the rock had actually failed. I don't know why my pointer is not working. Finally, it's working. So, what are the innovation of these structures that made it such a success, such an engineering success, and so long lasting? First of all, the concave elliptic frustrum, i.e., the iconic shape that nowadays we all associate with lighthouses at sea. It was Smeaton's idea. Another very important idea was the anchorage of the base rock by wave to the base rock by wave of iron bars and solid courses which could not be washed away by waves. The stone blocks were radially shaped and interlocked and very importantly set in Roman cement. Roman cement is what we nowadays call Portland cement or just cement, i.e. the base of modern concrete and reinforced concrete. At the time, it was entirely novel, the possibility of displaced setting in water and particularly setting in salty water conditions. Stone blocks were also connected to each other by way of marble dowels that you can see here in red and pink, and 3 nails, wooden pegs, which would connect one course to the next. In the rest of the talk, I will concentrate mainly on Wolf Rock. Wolf Rock is just outside the coast of Lansen, some 20 miles southwest at sea, where there is this red dot here. And Trinity House plans to build a lighthouse there since 1790. However, in the intervening 70 years, a number of beacons were built, but they were regularly washed away during the stormy season. The last of this beacon, which you can still see in this picture, was built by an engineer called James Walker, which was the head of engineering at Trinity House, and later on became a president of the Institution of Civil Engineers. And he was tasked in 1860 to draw plans for a new lighthouse. He benefited from already having engaged in lighthouse building at Bishop and Les Sanois, which were in slightly more sheltered conditions, but they were also a smaller enterprise. And he also benefited greatly from suggestion from his predecessors, Mr. Douglas, which had contributed to build Longship and also Bishop Rock. The Wolf Rock was also the first, 100 years later, to receive an helipad, i.e. a means for helicopter to land directly on the lighthouse for maintenance purpose and to bring livelihood to the then lighthouse keepers. How could we build and how can we study these structures? We have a wealth of archival information that has arrived to us through Trinity House and the Institution of Civil Engineers. And the study of this information reveals that there were important improvement of the Smeaton blueprint made by both Walker and Douglas. The most important improvement was in relation to the vertical dovetailing, but also the fact that they changed the timber pegs with galvanized bolts connecting the lower courses. The wealth of information that we have, which consists of basically the very detailed drawing of each single stone for each single course, allowed us to build 3D CAD models which represent each stone in each course, up to determining the whole geometry of the structure. And this, of course, then allow us to a very important step towards the analysis of the behavior of the structures underway. However, in building the structural model for a lighthouse, which is 35-meter high, made of granite interlocked blocks with a construction that has 16 radial blocks and 12, and then reducing to 12 when we go to the higher level. This, of course, create very complex shapes and geometry, which are sometimes difficult to reproduce in a mechanical model. In engineering, we use either finite element models or what we call discontinuous models, which is what I will talk about in a minute. One key important element here is the fact that although these stones are set in mortar, the mortar is much weaker than the stones themselves. and they are almost dry joints after 200 years. So in fact, the stones are able to move and detach from each other. And therefore, it is important to simulate that detachment and separation of blocks in order to explain the actual behavior of the structure. For these reasons, we decide, yes, to keep the modeling of each of the blocks as a separate entity, but we concentrated on the vertical keying that that I had introduced earlier, without particularly introducing also the marble dowers or the dovetailing in the horizontal range. This is because while the dovetailing in each horizontal course is fundamental during constructions, once the ring is completed, it will act as a unique object almost, and hence we don't need to model that separation so much, and we can simulate it with with a simpler geometry, another trick of building mechanical models. So that said, then we need to consider what are the wave forces that we can apply to these structures. So this type of waves that you see in this picture, they're called plunging waves. And as I mentioned earlier, at Plymouth University, they did very accurate analysis of their distribution and return period, probabilistic analysis of over 250 years return period wave for the particular location of Wolf Rock. The type of impact is obtained by using a theoretical model produced by Wenck and Umeraci in the 1970s. And as you can see from these, there is some problem with the laser pointer, but as you can see from this diagram, basically the all impact has a duration of 700 of a second, and but the maximum force associated to that impact has a magnitude which is proportional to the weight of the same order of magnitude of the weight of the lighthouse. What creates the forces is not so much the water breaking on the lighthouse, but the compressed air before it, preceding it. So it's important to identify the area of impact, and it's important to understand how the lighthouse will react to such impact. So two mechanisms can be identified, either sliding or overturning by basically part of the lighthouse rocking over the top of the rest. These two mechanisms had already been identified by Douglas Jr., son of the Douglas Sr. that had designed the previous lighthouse, which said in 1884, a lighthouse tower might be destroyed in either of two ways, either by being moved bodily by the sliding at the base upon its foundation, or by being fractured at some point in its height and the upper portion being overthrown. So how we can represent this from a numerical point of view? So we can use what we call limit analysis to calculate the critical uplift, and this so assuming that this is the way in which the structure will respond. Sliding is typically prevented by the vertical key that we have seen before. So the most likely possible way of failure is the rocking. We can, with limit state analysis, determine this blue curve, which identifies for height of impact and increased force, the area under the blue curve, which would be a combination of weights and height of impact, which are safe, so the structures will not be rocking. But for positions above that blue line, then the rocking will occur. If that is the case, then our particular wave force for the 250 years of return period is represented by this yellow diamond over here. And clearly we have cause for concerns, because it would not only start rocking, but the force is way above and applied very high and above the so-called safety curve or static curve. So, however, what we know is that the behavior, once it starts rocking, is much more complex than just the rocking around one point. And given the distribution of inertia of the lighthouse, the behavior is such that there will be more than one hinge, and that at least two portions will be rocking relatively to each other, forth and back. This is not easily studied with analytical model, and equations can be written, but they cannot easily be integrated in a solution found for each instance of the rocking. So that's why we have resulted to the numerical model that I mentioned before. Before looking at that in more detail, however, it's interesting to think about which of the lighthouses is most prone to rocking, so for which we need to be more concerned. In order to determine that, we make a comparison between Wolf Rock and Les Anois, because they are relatively similar, although their scale is quite different in size. If we look at that blue curve that I had identified before, and here they are reported for Wolf Rock and then for Les Anois, we can see that Les Anois has a much smaller area of safety with respect to Wolf Rock. And we can also see that the base of the tower is much shallower. However, and this is the impact wave that we have considered earlier, so just for reference. However, if we then consider to use a dimensionalized approach, i.e. we divide the height of impact by the height of the tower and the force of impact by the weight of the tower, we find out that the two curves almost coincide. But of course, the force has a different proportion with respect to the curve. And again, Les Anois appears to be at greater risk for that level of wave and application and point of application than Wolf Rock would be. But what is interesting here is the fact that the two curves lie on top of each other, which means that the Douglas had actually designed all of this building in almost a parametric way in very modern time, and they were able to scale them up and down to basically determine very similar performance. And this is a very modern way of thinking about structures. Let's go back now to the modeling and look at what happens when the force is applied to the lighthouse. You can see the opening of some of the joints here, and at the same time in the lower part. And these openings will be on opposite side of the tower, so on the windward side and on the leeward side, respectively. What is interesting to see is that the actual opening it doesn't occur only on one joint, as we had assumed in the simplified model, but it occurs on a number of joints, as we can see reproduced here, which means that for each of these uplift and downlift, there will be frictions between the stones, and there would be rocking occurring and dissipation of energy. This dissipation of energy is actually extremely important in making so that the wave have a much lesser impact than they would otherwise be if the response of the structure was purely elastic. If all the stones were solidly connected and the lighthouse had to perform as a simple cantilever. But are these impacts critical for the lighthouse, and would they take us to failure? So let's first look at the horizontal displacement. Here we can see that for the period of impact, the upper part of the tower has a negative displacement, so it goes backward, and then it comes forward again after the impact is over, and has a total horizontal displacement of about 23 centimeters, 0.23 meters. The effect of the dissipation of the energy is such that the next crest, it's only 0.04 meters or 4 centimeters. So there is an 83% reduction of that movement. And as I said, this is critical because this within the time of 1 second, because this gives, basically makes so that the next wave incoming, if it's of a similar magnitude to the previous one, it will find a structure that is again at rest and ready to take the next wave, rather than a structure that is already deformed, and hence the effect of the train of waves could be cumulative. The next question is, how does climate change affect the structures? We, again, at Plymouth, they looked at what would be the difference between the wave calculated for the condition of sea level at 2017 and in 50 years time. We can see that the duration of the wave is slightly shorter, but we have a greater force of about 10% greater, and about slightly higher up on the force resultant point of application. The type of wave is the same, and we can see from the analysis that we have an increase in the total vertical opening of about 20%. So although the wave is not very different, but, and of course there are uncertainty in relation to the magnitude and positions and all the parameters that characterize this wave. If we make comparisons, we can see that the actual results is much greater than and this has to do with the fact that the wave will hit higher up on the lighthouse. What that means for the single joints, and again, will that mean that we will have failures of some of these joints? So here we can look at the actual displacement of each of the joint, which is of about 2.3 centimeters or 23 millimeters for the case of 2017, and about 25 millimeters for the case of 2067. It's important, it's interesting to correlate this with the depth of the vertical keys, because remember, are the vertical keys that are preventing the upper part or any joint from sliding from the upper to the lower one. Therefore, the fact that this total opening is smaller by a factor of 3 to the actual height of the key means that they will not be sliding, and that as long as the wave has a relatively short times of a period of impact, the structures will still be safe. And it's interesting to see that the factor of safety here is quite high. Indeed, it's about 3 times. It's about 3. So again, if we think about the design of these structures, they were definitely very well thought over. So in conclusion, the use of the historic information is fundamental to build an accurate, advanced numerical model that can really represent the behavior of the structures. Of course, we have many uncertainty about the actual wave actions, because this is a probabilistic and random magnitude and intensity of impact. The vertical keys we have seen that are fundamental to explain the reliability and the integrity of these structures, and explain why they have survived for the past 200 years, and hopefully they will also survive another 200 or 250. The limit analysis is very useful to predict thresholds for intense rocking, and the fact that when we adimensionalize these curves, we have basically one that represents a whole family of lighthouses, means that Douglas had a very good understanding of the relevant importance of the different design parameters, and that these were scaled up and down for the different lighthouses in order to meet the same requirement. There is substantial energy dissipation, as we have seen, during the rocking due to local impact between blocks and frictions at the contact interface. And this is fundamental to the lighthouse survival, so that subsequent waves will not impact on an oscillating object. For this reason, the accurate impact duration and its magnitude variation with time is of primary importance. And at Plymouth University, they have a large oceanic basin, and they have actually studied these particular aspects in great details during this project, to better understand the interactions between waves and duration of impact, magnitude of the impact, and point of impact on the lighthouse. And this has shed quite a lot of insight in the response of these structures. Thank you very much for listening. Any question?
Thank you very much, Dina. This has been fascinating. I like how this project has many of the key elements of heritage science projects, in the sense that it involves an element of historical understanding with engineering principles. And I found this interaction super interesting. I'm sure there will be some questions from the public. I'd like to remind you that when you type the questions, it would be great if you could also mention your affiliation, your institutional affiliation, if applicable. That would be very useful. I see only your names. The first question that appears, Dina, is whether, given that you used real drawings or historic drawings, was there any issue of interpretation, or perhaps some divergence between the observations of the real lighthouses and the drawings? Did the fact that there's a layer of interpretation of these historic documents add any uncertainty to the research?
Yes, there were, of course, details that were that we had to clarify sometimes on site, and but by large, the drawings were very accurate, and these are what we would call today as-built drawings. So they were, you know, as I said, each single stones for each single course is drawn, and of course, you have seen the integrity of the lighthouses in the few pictures that I've shown. It is impossible to look in detail inside the thickness of the walls to determine whether they have exactly been built with all the dowels in the correct place. But we do believe that the keys, that all the stones were shaped with the correct keys and so on. And certainly the position of the joints and everything else that could be studied from the external fabric corresponds to what we see on the drawing, if that answered the question.
Yes, thank you. Would there be any other questions from the public? In the meantime, I have one of my own. I find the different elements of the research very interesting. So this probabilistic approach to let's say extreme events or dangerous events, and then
yes,
the use of the parametric analysis of their consequences and so on. And I cannot avoid thinking that the same process could be applied in other phenomena, in analyzing other phenomena in heritage. And I wanted to ask whether you would have any thoughts of this. Do you think this kind of approach could be applicable to other contexts? And if so, what should be ready before we do? What are the elements that need to be in place? What are good candidates for this kind of research?
Well, I think there is, if we just look at climate change, I mean, I personally have done quite a lot of work in earthquake engineering, and in earthquake engineering, you definitely use probabilistic approaches to determine the possible acceleration on any structures, and even more so on heritage structures. And there are again large uncertainties in the characterization of the actions. With reference to climate change and environmental events, the issue is always that when we look at heritage, we are not interested in the worst average event, but we are interested in the worst extreme event to a certain extent, because we are looking at long return period. And one of the issues with the long return period is that let's say the tail of this distribution very often are not as well characterized as the larger part of the bell-shaped curve if it's a normal distribution. So that is and that's where we need input from statisticians, but also from scientists and physicists that have actually studied this phenomenon in detail, and that can provide good strategies for characterizing this phenomenon. But also we need to think at how that particular piece of heritage will evolve in 200 years. Yes, because very often we looked at something that has been there for a long time, and we wish it to be there for a similar long time, unchanged. But when we look more at the history, it's not and it is the case also for the lighthouses to a certain extent, we then identify moments in time where that particular piece of heritage has changed significantly. And so, as well as projecting the effect of actions in 200 years, we should project the possible changes to the structures or to the objects in 200 years, which very often are man-made and have little to do with natural hazards.
Thank you for this answer. We have a couple of other questions. One from Tobit Cortez from Tobit Cortez Associates. He asks, some of the historic land-based lighthouses are rendered. So South Foreland, for instance. These examples appear not to be. Is there any issue with water penetration into the core of the structure that could destabilize the system?
That's an interesting question, because we also thought that that can be a very important variable. However, these structures are made of granite, and they have, and as I said, they are very modest courses. And although there is, of course, they get wet, but during those events, we don't, Trinity House has continuous maintenance journeys and inspection to these houses and to the lighthouses, and the level of deterioration of the granite is very modest, where there might be some localized minor crack and some loss of mortar, but this is over very long time.
A related question by Paola Blasi asks which were the most used types of granite and whether these were local types.
Yes, usually many of these lighthouses are are off Land's End and in the area between Land's End and the Scillies, because there are many outcrop of shallow rocks in that area, and the granite comes mostly from Cornwall. So they were, let's say, relatively local, yes, but they were shipped from mainland to the outcrops. And that was also one of the issues, because it so happened that sometimes the ships with the granite would be washed away during constructions or being thrown to the rocks during a storm.
Thanks. There are many questions coming through, and the one that has been waiting the longest is by Scott Orr, academic at the Institute for Sustainable Heritage. He asks, how could the changes in impact on these structures throughout the 21st century, so the changes that you projected, how could they be communicated as risk?
This is a very interesting information, very interesting questions. We have worked throughout the project with Trinity House, and Trinity House is very aware of the risk that these structures are exposed to. It very much depends on the stakeholders that you work with and the level of awareness. Usually, in my experience in working, for instance, in other contexts on flooding and again earthquakes, the risk is easily perceived once it is discussed, and it's even more perceived when an event happens, such as, for instance, my experience in the Philippines, where they had an earthquake and then a typhoon in the space of 6 months, and many churches were destroyed as a result. So there is, I don't think that there is an issue on communicating the risk as much as there is an issue on clearly identifying mitigations measures which are realistic and implementable, and also determining ways in which the cost of these implementation now can be understood, even if the benefit will be felt in 30, 50, or 100 years. I think this is in the present, let's say, society and economy, I think that's the major point of friction.
Thanks. Another question from Catherine Curran, academic at ISH. Could you speak a little bit more about the shape of the curve of force of the wave over time? It seemed to drop off very abruptly. Why was that?
Well, this is, as I said, this is also an interesting question. This is the theoretical model developed by Umerici and Wienke, and is a typical impulse impact. What we have seen in the, what our colleagues have studied in the ocean basin shows that the actual impact is more gradual. So the one that we have used for our simulations is more of a blast impact, let's say, and it's, as we have said, it's produced by the air preceding the wave rather than the water itself. It's very difficult to understand the difference between the two, as we have put instrumentation by the University of Exeter, and Professor James Brown-Jones has put instrumentation on a couple of these lighthouses, and we hope to be able to register acceleration and displacement that will actually tell us how long those impacts are and what is the response of the structures. We also have geophones and other instrumentation that is able to actually record the waves themselves.
A question from...
I'm not sure that completely answered the questions, but...
If it didn't, Catherine, feel free to comment. Is there any significant damage caused by friction or collision between the stones while they're moving? And are there strains in the vertical direction in the stones while they are moving? Okay, so as we have said, the assumptions is that the stones are largely rigid and just connected with each other through the key. And the stones, and there is a movement of opening and closing, which means that they will exchange frictions, and that friction will generate strains and stresses within the stones, but they will not be pulled and there will be some compression when they hit each other again. So there will be some level of stresses. However, the level of stresses is relatively modest with respect to the capacity of the stone. And in our analysis, we have not included the possibility of the stone block failing under impact against each other. And finally, a question from Alejandro Albuerne, also academic at ISH. Are there older lighthouses standing in the same region? And if there are they different significantly in their construction or in their exposure to tidal loads? So we have studied 6 of them, and 4 of them are relatively close to each other. One is in Scotland, and the other one, Fastnet, is in the Irish Channel. So they are not all the same, all in the same region, and
there are another, I think, there are more than 20 of these rock-mounted lighthouses around the British coastline. They are not significantly different from each other. They are designed relatively similarly. And as I said, that shape has become quite iconic, and we almost identify the lighthouse with the shape of the Fostrum. And this is because they were, they were an engineering object, and hence they were designed with engineering in mind and to respond to a particular and to fulfill a particular use and role. The tidal range has importance up to a point, because it's the pressure produced by the tidal range, if there are no weather storms, is not particularly critical for the capacity of the lighthouses.
Excellent. Well, thank you very much, Dina. And I think that with
thank you for the many very interesting questions, which give us more ideas. Just to say that we are not stopping working on lighthouses. We are now with Trinity House looking at the next 100 years and looking at how we can improve the helipads that were introduced on many of them in the 1970s and 80s, and they are now 40 to 50 years old themselves, although they were new then, and they are wearing out, and we are looking at how to replace them in the future with novel materials this time, rather than
forward to an update.
Yes, exactly.
And thank you very much, Dina. Thank you very much to everyone who has attended and asked questions. If this was a normal year, now I would be inviting all of you to come with me to the second floor and have some wine and keep discussing with Dina. I hope we can do that at some point close in the future. I would just like to finish reminding all of you to check out the program of lectures. The next one is already advertised by Jürgen Huber from the Wallace Collection on energy efficiency in their collection. That will be on the 26th of November. So it will always be towards the end of the month during the whole of this academic year. I hope to see you all then as well. Thank you very much for coming, and see you soon.
Thank you everybody for listening, and thank you, Joseph, for inviting me. Goodbye.